The Sunrise team welcomes you to another video that is part of a series which explain results of the use case 1.3 cooperative perception testing that demonstrate the successful application of the Sunrise Safety Assurance Framework. This use case evaluates the perception layer of an ADS in urban non-line-of-sight scenarios using V2X communication. It focuses on collective perception messages, CPMs, to enhance detection of pedestrians occluded by parked vehicles. 3 parts of the SAF assisting in the safety case building will be demonstrated, namely, allocation and execute part of the environment block as well as the test evaluate part of the safety argument block. In this demo, we evaluate the perception layer of an automated driving system deployed on a real vehicle operating within an urban environment. The scenario takes place on a 2-lane straight road segment, where parked vehicles on the roadside create visual occlusions. At a pedestrian crossing, a vulnerable road user, a pedestrian, suddenly appears from behind a parked vehicle, simulating a darting out situation. The demo showcases how the system under test, enhanced by cooperative perception through V2X communications, detects the occluded pedestrian using cooperative perception messages, or CPMs, sent by nearby connected vehicles. This extended perception capability allows the ADS to see beyond its direct line of sight, increasing the safety window and enabling timely action to avoid a potential collision. As shown in the right side, we developed a hybrid test framework. The ADS OBU test tracked are real. Parked vehicle, pedestrian, oncoming vehicle are virtually simulated. The perception the oncoming vehicle is simulated virtually. The virtual simulation interfaces with the real devices using MQTT broker server. This demo illustrates a safety test case by building safety evidence through detailed evaluation of individual scenarios using binary pass/fail criteria. It produces key results, including an initial allocation to virtual testing, followed by a reallocation to hybrid testing, culminating in a final allocation structure diagram. A hybrid co-simulation framework developed especially for this UC is being executed where virtual simulations interact in real time with a physical vehicle on a test track. It safely simulates critical pedestrian scenarios, including potential collisions, by modeling the pedestrian virtually, thereby reducing on-road testing risks. The demo adopts a modular setup where the ADS and V2X systems operate independently but collaborate effectively. The simulation outcomes are validated through hybrid testing. The demo begins by validating the allocate phase of the SAF. Following this flowchart, we start by identifying the test case requirements and conducting virtual simulation tests. These requirements are then compared against the capabilities of the virtual testing framework to determine which aspects can be evaluated virtually and which require a hybrid setup. We now present the virtual simulation based on the initial setup. As the ego vehicle approaches a pedestrian crossing, another vehicle, V1, comes from the opposite direction. A red parked car creates an occlusion, hiding the pedestrian from the ego vehicle's view. However, V1 detects the pedestrian and sends CPMs with this information. The ego vehicle receives the messages, slows down, and reacts safely, highlighting the benefits of cooperative perception. A safety-critical scenario occurs when the CPM is not received within the necessary safety window. This scenario is same as when CPM connectivity is absent. In this case, the ego vehicle is unable to perceive the occluded pedestrian until the pedestrian emerges directly in front of it, leaving no time to react and avoid a collision. This highlights the importance of CPM connectivity to ensure effective collision avoidance and pedestrian safety. After the virtual simulation, we compare test case needs with tool capabilities. Urban road, modeled via Sumo's detailed network. Dynamic elements. Sumo simulates vehicles and pedestrians. Occlusions. Parked vehicles modeled in Sumo and visualized in vanes. V2X. CPM vanes support CPMs at 10 Hz. This confirms partial coverage and identifies areas needing hybrid testing. Initial allocation summary. Virtual simulation with Omnit++. Vanes. Sumo meets some test requirements but has limitations. Dynamic elements, connectivity, and positioning reallocated to SHIEL. Environment, weather, particulates, and vehicle dynamics reallocated to real testing. These reassignments form the final hybrid allocation combining virtual and real components. Here is the final allocation structure. Blue components represent simulated elements, red indicate real-world parts, and gold are hybrid components. The subject vehicle, its driving functions, and dynamics are all real, connectivity and positioning are hybrid, while everything else remains simulated. Thus, we validate the allocate part of the SAF through both virtual and hybrid XIL testing. Virtual simulations were used to prioritize safety and efficiency. With the final allocation structure, we will present demo videos featuring the real subject vehicle on the test track under real environmental conditions. Now, we demonstrate the validation of the execute part of SAF using hybrid testing framework. The virtual and real ground tests working together by communicating. In this video, we test the behavior of the ADS vehicle in a realistic urban scenario. As the real ADS vehicle approaches a pedestrian crossing, a critical hazard remains hidden. A pedestrian stands behind a parked car, completely occluded from the ego vehicle's line of sight. Meanwhile, in the virtual simulation running in parallel, an oncoming vehicle equipped with enhanced perception capabilities detects the pedestrian early. It generates and transmits a CPM to the ego vehicle. Upon receiving the CPM, the ego vehicle anticipates the hidden pedestrian and slows down proactively, allowing the pedestrian to cross safely. The rest of the scenario, including the pedestrian's crossing and the vehicle's continued interaction, is carried out entirely within the virtual simulation. The results obtained via the execution of the scenarios are evaluated in the test evaluate part of the SAF. We consider the time to collision of ADS KPI and the CPM delivery ratio and CPM delay as the connectivity KPIs. We compare the KPIs obtained from virtual and real components to validate the test evaluate part. VRU pedestrian safety. Test results from virtual and hybrid setups show good KPI correlation within safety thresholds. Short summary of limitations and future work. Latency issue. Delay between virtual and real components depends on network. Must be minimized through optimized interface selection. Scenario complexity. Future work should include multi-vehicle scenarios to assess interference effects and CPM drop rate impact on safety metrics.